Hi, today I want to talk about the second chapter from Designing Data-Intensive Applications, the book. My impressions about it. So, I love defining words, and Martin, the author, goes the extra mile to define words. So he's sure that we understand the words he's using, which is amazing. I haven't seen any other book give so much effort on word definitions and making sure that the reader understands the book. So let's start with the first definition, which is a data model. It's how info is organized, how information is organized and manipulated. For example, and this can be on many levels, many abstraction levels. So on highest level, if you're an application developer, you care about making transactions, uh, sales, moving money, uh, working with entities like users and real world objects. And you need to somehow represent them and manipulate these real world objects. Whereas on the lowest level, a hardware engineer, an electrical engineer had to think of smart ways to represent zeros and one into electrical signals. So his information was zeros and ones, and he needed to represent them as electrical signals, to organize them and store and manipulate them, these ones and zeros. And there can be anything in between, like in between the real world and the zeros and one. There are maybe in the middle, like database engineers that design the databases from popular vendors. And what they care about, they need to represent, for example, a SQL engineer might need to optimize the database to represent information in these columns and rows. Uh, so again, the word definition for data model is how information is organized and manipulated, stored and manipulated, whatever. Next off, he said that, SQL dominated for the last 25, 30 years, which is basically forever in computing. Also, later on, he mentioned that it's not about SQL versus NoSQL, which was a trend started 2010 somewhere, like hashtag Twitter for a conference, which actually means not only SQL. Uh, and my opinion about it that there's SQL and there's everything else clearly shows the importance of SQL as a data storage, as a general data storage, which is amazing. I initially thought that SQL was invented by some kind of scientist locked up uh, in his basement, and he was some kind of researcher, a genius. But it's actually not the case. I'll go back to that. SQL developed more naturally than I thought. I'm also reading sometimes from my notes. Also, another interesting thing, like I'm skipping some sections. Uh, I want to talk about the things that made me an impression and which I either haven't thought of or I didn't know. So the cool thing about SQL especially the joins, is that we represent other entities. Let's say we got users, we got schools, we got organizations in LinkedIn, for example. And we represent that the user is in a school with a foreign key. Let's say a user can be in one school. What's the school he's in currently? We can represent that with a foreign key to the school's table. So from the user's table goes a foreign key with the ID of the school. That way, when the school name or the school email or school picture changes, the changes are automatically reflected on the user's profile if we show the school. That's because the ID has no meaning to humans. So it doesn't need to change. It won't need to change. While things that have meanings to humans will probably change in the future. So I never thought of why is this ID so useful? Because I've seen it from practice. So yeah, basically the ID doesn't need to change because it's not human information. It's not useful to humans, so it doesn't need to change. And whatever is useful for people, for humans to read less info directly, will probably change. So let's say we don't embed the school ID of the user, but we embed the school name. Now, the school name has a meaning to people. They care about it. They didn't care about the user ID, but they care about the school name. And guess what? The school name will probably change. Uh, the school picture will probably change. So we'll need to update all the users with the school name. But if we add a ID, the ID doesn't need to change. Then the author talks about uh, the document stores first before SQL. And one of the drawbacks is that they're bad at normalization, which is another word. It means representing data in a single place. Let's say we have users and school names. So we got one user and he can be in many schools. What do we do? Like in SQL, we can have a schools table and a users table. So this way, they can point to the same school. If a user is in the same school as another user, they can just point where they join following. Whereas with MongoDB, you're not forced. Yeah, generally, you need to denormalize data. So you need to copy all the school info into each user so that you don't do joins in MongoDB, which is also another topic that all these NoSQL databases and SQL are merging, and NoSQL in many ways just reinvents SQL. Yeah, we'll talk about it. And especially, okay, so document stores uh, can be good, can be good for one-to-many, so one user in many schools, or one user with many nodes. However, it's bad at many to one because it's a tree. It's hard for many things to point at one record. One example would be many to one. Whatever. I'll think of an example later. And especially for many to many relationships, that's where when databases, document stores just die out. They're bad at it. When you have many users connected to many schools, for example. So in the sense, uh, in MongoDB you can also do joins, but they're limited. And in the sense, NoSQL is again reinventing, is repeating history. Uh, so a little bit of history. During the 60s and 70s, for the Apollo mission, they were using something called the hierarchical model. It's a tree structure which you traverse, and they had immense difficulties with many to many relationships. They either had to duplicate the data or perform complex joins in the application code because it's basically a tree and you cannot point. I I ain't got no idea when the video stopped. I basically talked about the 60s and 70s that the most popular model back then was the hierarchical model, a tree structure like JSON. But they had immense difficulties with many to many relationships in the Apollo mission, which used the hierarchical model. Many to one also, because you got a tree, and it somehow needs to point many branches to the same node, which could easily happen to be a graph, if you ask me. Um, so they either had to duplicate data, denormalize, or move the querying and joining of data into the application code. I liked how SQL developed. So I see it as people recognize that querying went outside the database almost always. So the application code had to do things the database was supposed to do, the data model. It was not some kind of revolutionary paper that went out and changed the world. No, it was clear problems. People needed to do joins. It needed to be solved. Of course, a lot of smart people uh, worked on solving this problem and research and so on. So after the hierarchical models, two models came out. First of all was the network model. It was like a linked list graph, imperative querying. You had to specify where to go to search. It got a lot of hype. And then there was the relational model. Yes, SQL. And the network model, since it was a linked list graph, it was an imperative. You had to specify where to go and keep track of where we were going. It was like traversing a labyrinth, a maze. Even the inventors admitted it was like navigating a n-dimensional space. It was too much. It probably went somewhere with another technology improving upon it, so I don't know. So now we got why SQL is the way it is about joins. It was because of necessity. People recognized querying went outside the database. They moved it back in. We'll later also talk why SQL is so great about the declarative language. Since it's declarative. Because it's declarative. Um, let's talk about document stores. So document stores are JSON-like objects where you can store data. Um, one of the popular use cases for them is schema flexibility. And a lot of times it's mentioned that they're schema-less. However, that's misleading. Your application will always have schema. It's either schema on read, like MongoDB. Your application expects some kind of structure. It does. Or schema on write, where that's SQL. It enforces schema when writing, whereas the other thing enforces schema on reading. Where document stores fall short is again many to many. It's pretty good for one to many because it's a tree. Imagine one node can link to many other nodes, one to many. And it's okay with many to one. It, it has foreign key reference just like SQL, but terrible at many to many. You'll see how is it running? You see how these document stores and SQL and other languages just converge. They're stealing stuff from each other. So MongoDB now will talk about foreign keys, which is a SQL concept, relational. So yeah, I prefer personally schema on write like SQL because you also enforce schema on read. Um, yeah, one of the bad reputations for schema is migrations, that they're cumbersome. Um, yeah, also I forgot to mention that document stores can be used not only for um, schema on read, no, the schema is that they don't enforce schema on the database level. They can also be used if you store um, different types of objects. Um, which I have no experience with. It sounds strange. Uh, so the trade for the schema in SQL is that you do have to make migrations. Um, they have a bad reputation. Services like Neon, I believe, have solved them with database branching and so on. I personally don't need any fancy tools just to do migrations. On the schema, because I haven't worked in a project with 1,000 developers working on a single database, so I don't know how that works. Um, but schemas have a bad reputation because of downtime. That's what I understood from the book. Apparently, when you do a schema migration and in a big company, there will be some downtime. However, all modern SQL databases perform migrations within milliseconds, and you don't necessarily have to shut down the database. With the exception of MySQL, I never knew that outer table was different from the other outer tables on the other SQL languages. Um, there are some cases in MySQL where you have to copy the whole table and it may take minutes and hours of downtime. However, appending columns doesn't copy the whole table since version 5.7. Uh, pretty old, yeah. Uh, they got that, so if you remove an index on a column, yes, you probably will have to uh, rewrite the whole column and change things to the column, but not the whole database, not the whole table. Which nice, it's MySQL. I love Postgres, so I don't have to think about that. Mm, about the document stores, one of the primary purposes where the schema shouldn't be enforced on database level. That also sounded strange to me. Like, you don't know what kind of data you expect? Well, what you mean? You you have no idea what the incoming data structure is. But then I realized it's not that you don't know. Maybe you don't know. That would be strange. I have no experience with that. However, you may know that the schema changes. And that was the one of the big parts of my mentor's job at the previous company. They had Shopify, which every 3 months changed the uh, products product fields. So you either had to change the columns every few months because they get removed or new ones are added, new properties to the product, or you just had to do a JSON. And they did a JSON field in Postgres, JSONB. Also, really cool thing, SQL is actually based on relational algebra. So if you've written in 8th grade or 12th grade one of those U signs or inverted U sign, which is union, intersection, or an element is in a range, an element of the E, the strange E with the brackets, curly and square brackets. For example, XE, so XE square brackets 510, which would be X is in the range of 5 to 10 inclusive. Yeah, that relational algebra, that's the lower level of SQL. SQL is built on top of it, really close to that. So whatever you see in relational algebra, SQL just makes it with English words. Amazing. I love relational algebra. Now, earlier I said that SQL is a declarative language. So what's the difference between declarative and imperative? Okay, I'll define these words. Declarative, you say what you want, the thing gives you what you want. The path in between doesn't matter to you. You just say you want all the records where the animal is a whale, and it will find them. However, it's not your job to prepare the steps to find them. It just gives you. That's declarative. Well, imperative, you define all the steps to find them. Instead of saying I want all the records where the animals are whales, you say traverse this traverse this table, then go to the other table, uh, filter all columns where it's not whale, and so on, all the steps in between. So SQL is declarative. You say what you want, it gives it to you. The implementation is handled by the database. That implementation is called the query optimizer. And it's a huge beast in SQL. I, I'll probably do an episode on it. It's a fascinating beast. To have a general query optimizer, and you only say what you want from it. Oh, the fascinating thing about this kind of abstraction for managing complexity. So one great tool for managing complexity are good abstractions. And now I saw how a uh, declarative abstraction is better than an imperative one. I'll show you why. When you when you have an imperative code like the network model, you say where you need to traverse. It's hard for the database vendors to make changes for optimizations because they don't know what function you use to find your way. It's really hard to change it without breaking somebody's code. You know, I, in a sense, also I was talking about MapReduce, which uses the map and reduce like in JavaScript. Um, it's not used anymore. Also, the author removed it from the second edition of the book. MongoDB used it, then it added its own declarative version, like SQL. So in a sense, the MapReduce stuff is the imperative version of what SQL does for aggregation and query. No SQL accidentally reinventing SQL, but in disguise. I won't talk too much about GraphDBs. In Hello Interview, they said to avoid them completely. Uh, Even Facebook uses MySQL for relationships. They use the tau model, but it's stored in MySQL, so they don't even use relate the graph databases. Like, I don't know about your use case, but the biggest social network on the planet doesn't use them. You do you. That's what I can say. Also, I'll talk about some databases left unmentioned. First, we got the full text search. It's common to use full text search databases alongside your main database or other databases. Also, recently, which was not in the book, vector databases became real hot. There's also custom solutions, extremely custom solutions like for the Large Hadron Collider particle physics, where they process hundreds of petabytes of data. Supercomputers used to query this data and they need custom solutions. Also, there's string similarity searches, sequence similarity searches, yeah. Um, like for DNA matching. So you need to match this long DNA sequence against other sequences which have similarity but are not identical. No database up until now can do that. Um, I believe it was called GenBank. Let me see. Yeah, GenBank. That's what the uh, DNA matching guys use. Uh, there's also that's about it. I'll wrap up with the most important stuff. So first of all, we talked about SQL. We, we mentioned what data model is, how to store and manipulate data. I gave a few examples with the high-level programmers, which think of users, uh, transactions, sales, and real-world objects and events, whereas the lower-level electrical engineers just need to represent those bits into electrical current. Uh, we mentioned that it's not a fight between SQL and NoSQL. They can be used together. Uh, we talked why IDs work so well in relational databases because they have no meanings to humans. So they won't change. Whereas things meaningful to humans will probably change. We said what normalization is, where document stores fall short, many to one, and especially many to many. We said that SQL didn't appear out of nothing. It came from the clear problem that querying went outside the database and they wanted to bring it back in where it belongs by doing joins in the application code. Neither the network model nor the hierarchical model. Okay, the hierarchical model introduced the pain of joins, but the network model didn't solve it as well as SQL. Uh, Schemaless is misleading. You either have schema on the read or on the write, and when you have on the write, you also have on the read. Uh, Migrations have a bad reputation. However, they're not that hard, and there are tools to mitigate that. Uh, in current SQL databases, there is no downtime when you do migrations change. Queries can be executed within milliseconds to change schema. Uh, we talked about how MongoDB introduced stuff from SQL, like aggregating and sorting and so on of query of data, mapping it, how it introduces joins, so it copies from SQL. And we also talked about how SQL has native JSON support, like in Postgres, JSON-B is great. You can query actual JSONs, actual documents inside Postgres, which for me is the best of both worlds. You have a relational database, and when you need uh, nested records within one row, you can do that. So SQL also copies from the document stores. Also, Postgres has one of the best vector databases. What doesn't Postgres have? Uh, so when schemas can hurt, when the data is heterogeneous, it's different. Or you have external systems on which you rely on that write to your database, and the the data structure might change. We said that SQL is based on relational algebra. Also, why using a declarative language as an abstraction, a declarative API like SQL or CSS is much better of an abstraction layer than imperative, since you can hide the implementation and that can go to the database vendors, and the actual querying stays the same on the application, even when the database drastically changes how it's queried. And you can do much harder and complex optimizations behind the scenes, because there are actually scenes. With imperative, there are no scenes. Also, declarative code parallelizes better, which is how CPUs today scale. We won't talk too much about graph databases. It's graphs in database form. Uh, because Hello Interview said not to use them when we do system design. Interviews and uh, even Facebook uses MySQL to store its relationships. And my biggest lesson from this, not that there aren't many, like for me personally, the coolest thing was, solving complexity is a big topic of mine. I'm fascinated in any tool that helps me fight complexity. I love simplicity. So from the last chapter, we learned that one tool for fighting complexity is abstractions for the APIs. So you hide some stuff and provide good abstractions like add to cart, make payment, like product. Because I'm coming from the e-commerce world. Make comment like a functional method and not just spirals somewhat duplicated code. And now I also learned one of the points of a good abstraction, a declarative one. Because you tell the user how to use it, what the user says what he wants, and you on the back end can optimize the query to be fast for your user without, and even if you drastically change the code behind the scenes, the user's query is still the same. He doesn't need to change it. There are examples uh, with CSS versus imperative JavaScript, whereas with CSS you say the fifth P element should always be blue with one line, and it basically does it. And when another element is added, then still the fifth element is blue, you know. Whereas with imperative JS, you have to traverse the document object model, and it can be really nested, many stuff before you hit the speed. Let's say this paragraph is really nested, and you have to hit the body, the div, the section, the main, then whatever, the fifth paragraph. You have to traverse it with JavaScript and make it the fifth. And when we add another paragraph element, we will have to rerun the function. So there needs to be a listener. Like it's a huge amount of code that you have to maintain. Whereas with CSS, you say what you want to happen. Like you say the result and it just happens. Really smart people can optimize how that result is being made, achieved, how that result is being achieved behind the scenes.